Hello and welcome back to a video series on MAT 1033 Intermediate Algebra. My name is Sean Perry. This is going to be video 18 in the series Properties of Inequalities. So the way the next few videos will work is we'll start with a discussion of some key properties of inequalities. Specifically, I want to look at what they have in common with equalities and what some of the key differences are. In the next video, we'll take a look at graphing inequalities in their simplest form and what the relationship is between graphs of inequalities and sets of numbers. And finally, in the last video, we'll look at solving inequality expressions, both simple inequality expressions and compound inequality expressions. Instead, I'll just ask your pardon and introduce the following axiom. So this axiom is called trichotomy, and like all axioms, it's something we assume about numbers, but we don't really prove. We just state this fact, and we hope that it's obvious. For any two real numbers, a and b, there's only one of the following three statements that's true. Either a is less than b, a is equal to b, or a is greater than b. That's it. Those are the only options. It's got to be one of those three. And we write that with these symbols. So one helpful way to remember which symbol is which is that the symbol will open towards the bigger number so that the bigger side of that wedge shape is facing the bigger number. So in this case, a is less than b, and the little tiny side goes towards the a, and the big side goes towards the b. But if you're like me and you're from Florida and your teacher told you this when you were very small, then and it never got out of your head, you think of the hungry, hungry alligator. So we say a is less than b because this hungry alligator is really hungry and he wants to eat the bigger number. This has been living in my head rent-free since I was a child, and now it's in yours. Ha ha ha. Unlike equality, where if a is equal to b, that automatically means that b is equal to a, with inequalities, something slightly different is true. If a is less than b, then that means that b is greater than a. So you can flip the direction, but you also have to flip the inequality. So saying that a is less than b or saying b is greater than a is really saying the same thing. Those two are logically equivalent. So I want to make a note about number lines. Even before we start graphing inequality expressions, I want to note that there is a relationship between position on the number line and being less than or greater than. If you're on a number line with the usual orientation, left is negative, right is positive, any number that's less than another appears left of that number. So in this case, I've drawn a and b on the usual number line. Doesn't really matter what they are, but we know that a is less than b because of its position here. So one thing that means is that big negative numbers are less than small ones, or less than any positive numbers. For example, we would always say that negative 10 is less than negative 2. I like to think of it as negative meaning debt. It's worse if I am $10 in debt versus $2 in debt. Likewise, 0 is greater than any negative number, and all positive numbers, like 1, are greater than all negative numbers, like negative 1 in this case. So one thing that equalities and inequalities have in common is this property called transitivity. We talked about the transitive property when we talked about the properties of equality. That was that if a was equal to b and b was equal to c, then we automatically knew that a was equal to c. Now, I want you to just meditate on this idea. If I know that a is less than b, and I know that b is then in turn less than c, well, then a must be less than c itself. A is sort of constrained to be less than c by being less than b, which is itself less than c. So stop and meditate on that. And then consider the following. If x is less than 2, is it also the case that x is less than 3? Yes. Yeah, because 2 is less than 3. Because 2 is less than 3, if x is less than 2, then we know that x must also be less than 3. Another common property that equalities and inequalities share is that you can add or subtract to both sides and still get a true inequality. Another common property that inequalities and equalities share is that you can add or subtract the same thing to both sides and get a true inequality. For example, if x is less than y, then x plus 3 is also less than y plus 3. And if a is greater than b, then a minus c is greater than b minus c, regardless of what c is, and so on. Another rule that works is you can multiply or divide by a positive number. If C is greater than 0, meaning C is positive, and A is less than B, then A times C is also less than B times C. And A divided by C is also less than B divided by C. But you probably notice from this caveat that the number needs to be positive that something else is going on with inequalities. We can't just do anything we want to both sides and still get a true inequality. Let's see why that might be the case. It's going to have to do with that sort of symmetrical property of inequalities and the relationship between greater than and less than. Let's just consider the statement A is less than B. We just saw that we were allowed to do the same subtraction on both sides, or I just asserted that that was true, and I hope you believe me. So I could minus A from both sides, and that would give me B minus A is greater than 0. This, by the way, is a nice expression meaning that B is greater than A if its difference with A is positive. But let's keep going. Let's subtract B from both sides. And then we would get minus B is less than minus A. Now, because we saw we could flip the inequality while flipping both sides, this means that minus A is greater than minus B. And factoring out that negative sign, we have that minus 1 times A is greater than minus 1 times B, putting the A and B back on the original sides again. But I want you to compare the first and last line here, right? Compare A less than B with negative 1 times A is greater than negative 1 times B. And you see we've done the same thing on both sides here, times by negative 1, but something's changed. We've flipped the direction of the inequality. And this gives us a nice rule. If we multiply or divide by a negative, it means you have to flip the inequality. Now, these less than and greater than symbols are called the strict inequalities. They exclude the possibility of equality. There are also non-strict inequalities. For example, this collection of symbols means A is less than or equal to B. This means either A is less than B or A is equal to B. Either one of those could be true. What it also means is that A is not greater than B. A not being greater than B leaves two options left that A could be. It could be equal to B, or it could be less than it if it is not greater than it. Likewise, we have this symbol, A is greater than or equal to B, meaning either A is greater than B or it is equal to B. And this could also be interpreted as saying A is not less than B. Not less than doesn't mean greater than. It means greater than or equal to, because equal to also means not less than. So there's two options when we say not less than, greater than, or equal to. So now let's collect all these rules and properties into some critical notes. I want you to copy this for your notes to prove that you watched the video. Let me zoom out so this is all in frame. There are 7 properties of inequalities that I would like you to copy down. We have trichotomy. One of these 3 statements is always true for any 2 real numbers. We have flipping the inequality when we flip the side that A and B are on. We have transitivity here. A less than B and B less than C means A is less than C. We have A less than B, means we could add or subtract C to both sides and it would still be true. If we have a positive number C, we could also divide or multiply by that on both sides and it would also be true. Finally, we have multiplying or dividing by a negative. Means we have to change the signs, yes, but also flip the inequality. And last but not least, here I have sort of the definition of the non-strict inequalities. So I should note that for property 2, 3, 4, 5, and 6, you could replace these with greater thans, or you could replace them with less than or equal tos, or greater than or equal tos, and you would still have true statements for properties 2 to 6. Okay, so now let's do the praxis for today. These are true or false statements. I want you to go through all of these and mark them as either true or false. Pause the video at this time and give that a shot. Okay, let's see how you did. So this one says negative 12 is greater than or equal to negative 2. That is false. all big negative numbers are going to be less than their smaller negative numbers. It's better to be $2 in debt than $12 in debt. If x is greater than 2, then x is greater than or equal to 3. Well, this might be true if I was only talking about whole numbers, but what about 2.5? What about 2.1? Any number between 2 and 3 will be bigger than 2 and yet less than 3. So this is also false. This is not true if we're talking about real numbers, although it would be true if we were talking about whole numbers. How about this one? X plus 1 is greater than x. Yes, that's true. That's true. If we go up by 1, we are strictly larger than where we started from. What about this one? X minus 1 is less than x, less than or equal to x. This is also true. In fact, it's going to be strictly less than it, but strictly less is included in this symbol, right? Just because there's an or equal to there doesn't make it any more difficult to achieve. If it's less than x, which this is, x minus 1 is less than x, then it's also less than or equal to x. Number 5. So we have 3 minus x is greater than 3. Is that true or false? Well, it would be true if x was a positive number, but what if x was negative 1? Then 3 minus 1 is 4, which is not greater than 3. So this is false when we consider all numbers, including the negatives. If we only had x positive, then this would be true. But it's not even true for the if we included 0. What if we had x was 0? 3 minus 0 is just 3, and 3 is not greater than 3. We would never say x is greater than x. That's a false statement always. Next, number 6, if 2 is greater than x, then negative 2 is less than negative x. This is true. This is the correct application of multiplying by a negative on both sides. You flip the inequality and the statement is still true. How about 7? If 3 is greater than x, then 2 is greater than x minus 1. Greater than or equal to, yeah. So let's think about what we have to do on both sides. To go from 3 to 2, I had to minus 1. And so really what's happened here is I've minused 1 on both sides. That's something I'm always allowed to do, so this statement is true. Finally, number 8, if a is greater than b and b is less than 3, then a is also greater than 3. Okay, think about that one. Now, if this had been a greater than symbol, this would be true. But this is not a greater than symbol, it's a less than symbol. And what about, so it's not true. Let's see if we can think of a counterexample. Take a moment right now and think of an example of a and b, numbers a and b, that would make this statement not true. Let's say, for example, a was 2.9 and b was 2.5. Well, then a is definitely greater than b. 2.9 is bigger than 2.5. And b is less than 3. But a is not greater than 3. 2.9 is still less than 3. So this statement is in fact false. A nice way to think of when you can have false statements involving variables is if you can come up with a counterexample. And in this case, 2.9 is greater than 2.5, and 2.5 is less than 3, but 2.9 is not greater than 3. So the idea that if we have true statements in the if thing, we get a true statement in the then thing is not the case in this particular example. Okay, that's all for this video. Thank you for your patience. Have a great day, and good luck with your studies. I will see you in the next one.